All right, welcome everybody. So you just turned in homework number 7, right? I previously referred to that assignment as kid stuff. Was I underestimating it, or is it all right? Pretty easy? In the middle? You didn't feel insulted by it, I hope. You didn't want it to be insultingly easy. All right. So the next thing that you've got on your calendar is phase 1 of the design project. Now remember, that's where what you're doing is you're generating flow estimates for each external and all of the internal demands for this hypothetical town, looking at issues like population density, fire flow, and all of the factors that maybe govern how much water they're going to need at each of those locations. And so you need to express it in terms of the summary sheet that I've given you, and then include the supporting calculations. They can be by hand, they can be Excel calculations. The one thing that I really would discourage you from doing is typing the calculations in Microsoft Word. I've just found over time that it's, Word's an awkward way to express numerical calculations. It's great for reports, but not great for showing your calculated work. So I'd actually prefer you do it by hand rather than trying to type up the calculations in Word. So
gotten one from Word before?
What's that?
Have you gotten one from Word before?
Almost every semester. Someone thinks they're going to go above and beyond and type their calculations, but it ends up being kind of a train wreck.
That just sounds a lot more work than what it's worth.
I agree. Yeah, I agree. And it doesn't turn out as nice either. So I just want to save you in case you're considering it. Also on Monday we're doing quiz number 2. And the coverage is just since the first midterm exam up to and including the lecture that we're going to have on Friday. So I haven't decided what the question will be yet, but we're going to have that quiz on Monday, and then your next homework assignment isn't due until Friday the 13th. And that's going to include topics from both Chapter 11, which we're still working on today, and Chapter 12, which we'll get to beginning on Friday of this week. So any schedule or announcement related questions? All right, we're going to work 3 examples today. The first one is just to refamiliarize ourselves with Manning's equation. I've already explained that the trapezoidal geometry is pretty common, and because of the geometric parameters having to do with area and wetted perimeter, it's kind of complex. But what we haven't done yet is use Manning's equation to estimate what the flow rate would be in a trapezoidal channel if we know the flow depth. And that's the case we have here. We're assuming that this channel is paved with smooth asphalt. It's trapezoidal and having a bottom width of 3.5 meters. The side slopes are defined 2.5 to 1. And the depth of flow is 1.2 meters. Now the S value that we're going to put into Manning's equation is 0.001. So remember here that the S needs to be expressed not as the percentage itself, but as a decimal reflection of the percentage, so 0.001. Now, rather than going to table 10.1 and just looking up the equation for wetted perimeter and area, let's just this once try and calculate it based on the geometry that's given. Based on the fact that based on the given depth of 1.2 meters, so our bottom width is 3.5 meters, then the area is going to be the area of this rectangular section and then the area of the 2 side triangles, which if you put those 2 side triangles together is itself a rectangle. And so it's going to have 1.2 meters for this parameter. The question is, what length do you have there if the side slopes are 1 unit of vertical for 2.5 units of horizontal? So we need to know the area, we need to know the wetted perimeter. And the wetted perimeter is going to be this length on the side, the bottom width, and then the side length again. And you can calculate that by it being the square root of the sum of the squares. So once you know this top width on the side triangle, then the depth squared and that parameter squared added together, the square root will give you the length of each side. So let's use Manning's equation to find out what is the flow rate. Where we know the end value, you'll have to calculate the area and the wetted perimeter, and we'll also factor in the slope. Okay, so here on the whiteboard, I've given you kind of a hint of what we're doing for the area. The area has two components. It has the rectangular component of the channel, so the 1.2 meters by 3.5 meters is this rectangular section. And then, since we know it's 2.5 to 1 on the side slopes, that means that if it's 1.2 meters of height, then this distance over on the side is going to be 3 meters, because it's 2.5 times 1.2. So if the depth is 1.2, then this width of the triangle will be 3 meters. And so if you put these two triangles together, then it's essentially a rectangle that's 1.2 meters by 3. And so there's the middle part and then the two sides together for the area. And then the wetted perimeter is going to be the bottom width of 3.5 meters and then 2 times the side length. And the side length here, the hypotenuse of that triangle, is going to be the square root of 1.2 squared plus 3 squared. So if we find the square root of that, what we should get for the area is 7.8 meters. And for the wetted perimeter, the distance should be 9.9622 meters. Okay, so once you have those geometric parameters, then you can substitute it into Manning's equation to find what flow rate should we expect for this depth, slope, roughness value, and geometry. All right, so with the area and the wetted perimeter calculated, we can substitute that into Manning's equation. Remember, strictly speaking, Manning's equation is just to calculate the velocity. And so I've multiplied Manning's equation by A in order to get the flow rate. And that's why we have the area to the 5/3 power, is that normally it's the hydraulic radius to the 2/3 power, and then we multiply it by the area to turn the velocity into the flow rate. But I've just combined both the area to the 2/3 power and the area to the 5/3 power here in the numerator. So the flow rate that you should get is 14.97 cubic meters per second under these circumstances. So if you're going to have a higher flow than that, the question is it okay for the water to be deeper than 1.2 meters? You know, it becomes a juggling act at this point. If you can't have the depth be more than 1.2 meters and this is the flow rate, or maybe you'll see more flow, then you need to make the channel wider to increase the conveyance. That's something a hydraulic designer can affect. Generally, what you don't have direct control over is increasing the slope. Although you sometimes can decrease the slope if you lay out a meandering path. You know, if you have location A and location B and the water's going from A to B, you can't make it any steeper than the elevation difference divided by the direct path length. But if you have the channel going back and forth, just kind of like how you'd ski down a hill side to side, then that increases the path length. And so the delta Z divided by the length, the L would be larger, and then that would decrease the slope. So normally a hydraulic designer, really what you have control over is the material, so that affects the end value, and then you also have control over the geometric shape and the width of the channel. Flow rate is something that's usually given or a result of things like storm conditions. So any questions on this example that we're using to calculate the flow rate from an observed depth? Okay. So the trickier thing by far is to calculate what depth will you have for a certain flow rate. What we've just done is relatively direct and straightforward, but the tricky thing is rearranging this. If we're going to solve it with the solver, then you don't have to rearrange the equation algebraically. You just type everything in terms of y. But if we're using Excel, like was demonstrated in class previously, the technique there was to move all of the constants to the right-hand side of the equation and then start with a guess value of the depth and see what depth does it take until the left-hand side and the right-hand side are equal and there's no difference between the two. But I told you that it's unavoidable that you have to learn how to do it on your solver of your calculator. I'm going to show you with this example, this next example, what it would look like if you solved it on the calculator that I wish you owned. I wish you owned the HP 50G, and in fact I was considering making it a requirement for the freshmen who enter Marshall next year, but what I just learned the other day is this calculator's been discontinued. Yeah, so
That'd be a fun requirement.
yeah, they'd have to buy, I don't know, from like an overstock place. I mean, HP still does make a calculator that's awfully good, but I don't have one, and I don't know. It's the new HP calculator is called the HP Prime, and I think it's targeted more towards the education market, where the HP 50G was directed at engineers specifically. It was less about the education market and more about engineers. So, all right, let's take this trapezoidal channel, and we're going to put 29 cubic meters per second through it. We know the bottom width is 3.5 meters. The side slopes are 2.5 to 1. So this is a bed slope of 0.1. This is the same layout as the example that we just worked. In the example we just worked, though, what we had was a depth of 1.2 because we had a flow rate of, what was it, about 15 cubic meters per second in that example. So what if we take the same channel and instead of a flow of 15 cubic meters per second, what if we put 29 through there? The question is, what is the depth? So let me show you why I wish you had the HP calculator, because I think entering the equation is so much easier on that calculator. It has a numerical solver where we can go into that numerical solver, and it's got a menu. It can do things like financial calculations, solve polynomials, differential equations. We'll just do the normal solving of an equation here. And the real magic is the way that you write equations. And so I'm going to enter this equation writer, and then I start typing the equation just like it's found. I don't have to reassign the variables, kind of like Dr. Pearson's demo video that I showed you in class last time. In this case, what I can do is I can actually say the Q is equal to, now I'm going to start typing in the equation in terms of, for a rectangular trapezoidal channel, the area is the bottom width times this parameter t times the depth times, I'm just going to basically be entering this equation in now. So Q equals, putting in the parentheses here, B plus Ty and all of that is times y, and all of that is to the power of 5/3. And this is why I like the calculator, is it actually creates the equation visually the same way that you see it on the page, and you don't need quite as many parentheses. So s to the power of 0.5. Oops. I don't know if I'm going to be able. Okay, s to the power of 0.5. And all of that is divided by N times B plus 2 times Y times 1 plus T squared By the way, you still could get this calculator. I mean, I see how it's on Amazon. They're not making anymore, but they're not completely sold out. So if this demo just makes you wish, wow, I got to have that calculator, then I would just be delighted to see you with one. To the power of 0.6667. All right. So that's the equation that we've typed in, and now once we do, it's going to create all of the variables, and we'll put in the flow rate is 29. Okay. The bottom width is 3.5. Okay. The T value, which refers to the side slopes, that's 2.5 units of horizontal for every vertical. Okay. The Y we're solving for, so we don't know that yet, but we do have the N value. Okay. And let me go down here and define the slope, 0.001. All right, so now that everything else is solved for, then I can click here to solve for the depth. So these menus up above here give context to the function buttons below them. So I'll click on the solve button, and it says that the depth is 1.57 meters. So that's how we do it with the HP. I want to see that you can do it on your Casio. So let's solve the same problem where we got 29 cubic meters per second going through this channel. Here's the equation you need to put into your Casio, and you're going to be solving for the depth Y. All right, so here is the equation translated into Casio speak, and what we're going to be solving for is the depth. Same channel geometry. Let me write the factors on the whiteboard since they won't be on the screen with this up. So we've got N is equal to 0.014. The slope is 0.001. The Q value that we're sending through that channel is 29 cubic meters per second. The T, the side slope, is 2.5 units of horizontal per vertical. And the bottom width, B, is 3.5 meters. And we want to find out what is the flow depth under steady uniform flow. So what's the normal depth using Manning's equation? The other thing that's pretty cool about, well, there's many thousands of things that are cool about this HP calculator, but one of the many things that's cool about it is it does units conversion. You know, for instance, if you have 55 meters and you want to know how many inches that is, you can go into length and convert the units. I mean, I don't want to demonstrate all of that, but it does units conversion, and it's great. Okay, so that's the second thing we've done today, is looking at how to calculate the depth for a known channel and a certain amount of flow rate. One of the reasons why we're interested in velocity through streams is that there is a certain amount of energy that's being exerted by the water on the material of the channel. And so you can see in this channel that there's been a lot of scour and erosion where the water is flowing, It's taking soil and can chip away at broken, fractured rock. Even if it's an erodible rock, the scour of the stream over time can wear away and kind of is more smooth than if it's lifting blocks up out of the water. But we can think in terms of the shear stress that's being applied by the water to the material. And remember, the relationship between the shear stress that's applied and the slope of the channel is dependent on the hydraulic radius and the unit weight of the fluid. Now, in Manning's equation, we can find the maximum allowable velocity by relating the slope of the channel and the shear stress. And so the way that we would fit these two together is that oftentimes through soil analysis you can find out what's the maximum tractive force of a soil. And that you can think of as the related to the cohesive strength of the soil, or what shear stress is going to cause the soil to begin, the grains to let go of each other and start to move independently. So if we have, in this example, a maximum shear force of 10 newtons per meter, and you know what the slope of the channel is, and you know, of course, that the fluid is water, then you would solve for an equivalent hydraulic radius based on the soil conditions, and then substitute that into Manning's equation to solve for the velocity. So let's do that in this example, just as an illustration of how you can use the soil properties in the shear stress equation to then tell you what's the maximum velocity in a channel.
I think Maggie's going.
Okay, so first we need to do is find an equivalent hydraulic radius. Now there's no physical significance. The hydraulic radius here isn't referring to any actual geometry. If you look at the problem statement, it never says what's the width of the channel. It's not talking about what are the side slopes or whether it's rectangular. So this R that we're finding here does have units of meters, but it's really just kind of a meaningless placeholder that's the ratio of the shear stress to the slope, taking into account the unit weight of the fluid. So when we do that calculation, we get that the equivalent hydraulic radius is 0.068 meters, and then we can substitute that value into Manning's equation and solve for the velocity of 1.02 meters per second. So any faster than that, and it's going to be applying too much shear stress to the soil, where the shear stress applied is greater than its cohesive strength, and the grains begin to separate and scour occurs, and over time the channel will become damaged, like is shown here. Any questions on this example? Okay, we have a little bit of time, so I'm going to bring up a picture of the network. All right, so here is the map for the design project. And I'm wondering, are there any questions related to the demand estimation stuff that you've been doing so far, things that have been uncertain or unclear? And if you ask it now, then maybe everybody would benefit from the insight and the discussion. Well, let me ask you a thought question. Oh, go ahead.
Elizabeth has a question.
Thank you.
You have the East Food Plan,
Yeah.
MG per week. What does MG stand for?
MG means millions of gallons. All right, so about that. She asked about, okay, there's a food processing plant in the East Zone. It's internal, so it's not an external like the cardboard box factory. But however much water they need in the East Zone for that food processing factory is going to be equally distributed between Junction C and Junction E. So how many million gallons per week is yours, say, is Elizabeth?
Mine is 2.5.
2.5 million gallons per week. Now the summary form, what units do I ask you to use for the flow rates on the summary form? Liters per second. So you're going to have a units conversion there, but you also have to think about time. So what you're trying to do is you're trying to figure out your design condition. And the residential uses, remember there's going to be the average daily flow and the peak hour flow, and then there's the peak day flow. And so residential is pretty straightforward. We use that curved figure that shows how the demand patterns change over time. But how would a factory use water, a food processing plant? If they're using 5 million gallons of water per week, in what way are they using it? Jeffrey?
Probably prepping the food and all that.
That's right. They're going to be using it to prep the food. Now think about the flow variation. How would, if it's a factory, it's not going to be like the water use in the factory has to do with people flushing the toilets and taking a shower or washing the dishes. It's an industrial demand. And factories are relatively constant processes. And so you can assume that it's a continuous flow. It's not going to be subject to peaking factors in the same way that the residential and commercial demands might be. But at the same time, you also need to be smart about over what time period is that water being used. Like how many seconds are there in a week isn't the same thing as how many seconds that factory is open. So the conservative assumption is going to be different from assuming that they're doing like 3 8-hour shifts that never stop. In other words, what I'm saying is that amount of water that you should be using, use that amount of water during 40 hours, not during however many hours there are in a week. Because if you spread out the water use over an entire week, what happens if they actually use that amount of water in 40 hours? So then the flow rate is going to be higher because it's the same amount of time, the same volume, but divided by a smaller period. So you want to be conservative, not overly conservative, but you want to be conservative. And so enable them to use their volume of water over the duration that's likely. So a similar situation at the golf course. Where's the golf course? Okay, here it is, the golf course. So you're going to find that they need a certain amount of water at the golf course. Why does the golf course exist? It's for people to golf for some reason. So I don't golf, but what I've noticed is that people don't golf when the grass is being watered. And so here's what you have to do is you have to figure out over what period is that irrigation water going to be applied. It's not 24 hours a day, 7 days a week. They're not going to be continuously watering. So there's a certain amount of water you have to deliver to the golf course, and the flow rate that you have to be able to support at this junction H should be related to your assumption on how many hours per week are they watering. Or they may be watering 2 hours a night, 3 days a week, and then you have a volume divided by time, and now you've got a flow rate. But the bad assumption would be to assume that they are watering 24/7, because your flow rate would be artificially low, and when you size this pipe according to that artificially low flow rate, but then they actually start withdrawing water at a higher rate, then the pressure drop would be unacceptably high. Sports stadium. You need to ask yourself, how much water is going to be used there and over what time period. So you can find data having to do with, if it's a football game, what water does each person use in an average football game, but you wouldn't then spread that out over 7 days a week. The football game happens during a 4 or 5 hour period on a Sunday, and so think not just about the amount of water is my point, but also think about the timing. And don't paint yourself into a corner by assuming that they're going to spread out their water demands over the entire week. Some of these locations may have concentrated water demands, whether it's the box factory or the food processing plant. So that's all I wanted to mention to you. Other questions that you've got at this point? All right. Well, that's it for today. We will continue on Friday, starting with some material from Chapter 12. So I'll see you then.